Hello everybody, welcome to lecture number 7. The midterm is next week, it's next Monday during our live lecture, and the midterm only covers material up through this lecture. So at the end of this lecture, all the material that we had covered so far to that point is fair game for the midterm. So today we're talking about indeterminate forms and L'Hopital's rule. So first, what it means to be an indeterminate form. So when you find a limit, an indeterminate form is an expression that doesn't tell you what the limit is or even if the limit exists. For example, let's say we had the limits as x approaches 2 of root x minus root 2 over x minus 2. And let's say we had the limits as x approaches 2 of root x minus root 2 over x minus 2 squared. Similar functions, but the top one is a linear power, the bottom one's a quadratic. Both of these, when you plug 2 into the expression, give you 0 over 0. That is an indeterminate form, because we have no clue what the answer is just based off that. Like we went over this the first lecture of the term. If this gave us like 3 over 0, then we know that the answer doesn't exist, but it's either negative or positive infinity. But 0 over 0 tells us nothing, because this means that there's a factor of 0 in the numerator and a factor of 0 in the denominator, and those two powers of 0 are canceling out all of our information. And it turns out, by the way, that this first one gives you an answer of 1 over 2 root 2 once you multiply by root x plus root 2 to the top and bottom. That gives you the cancellation of those two factors. Out comes your answer. This one gives you no answer. It turns out that this graph has a vertical asymptote at 2, where one side goes up to infinity, the other side goes down to negative infinity. So they both give that same indeterminate form, but gave us two very different answers. One existed, one did not exist. And there are 7 of these forms. So the 7 indeterminate forms are 0 over 0, which makes sense because those two factors of 0 are canceling out all of our information and keeping the limits answer hidden from us. It's also infinity over infinity is indeterminate. Either of these could be negative or both could be negative. Either way, that is indeterminate. It's also 0 times infinity. It's also infinity minus infinity. Also 0 to the 0th, also infinity to the 0th, and lastly 1 to the infinity. All of those are indeterminate, which again is only really applicable in the context of limits. So if you're taking a limit and you plug in the value that x approaches and it gives you one of these 7 forms, you have no idea what the answer is. You have to figure out how to algebraically rework the expression to go to find the answer. And some of these make sense, like the 0 over 0, the information's hidden, but some aren't quite as obvious. Like this one down here is usually what trips students the most. So I'm going to explain all 7 of these, and what I'm going to explain is that all of these are essentially just 0 over 0. All of these, when you do some algebra to them, give you 0 over 0. They're all just different versions of that expression right there. So they all come down to a factor of 0 that cancels out all of the information. So let's check this out. Let's first do infinity over infinity. Actually, before we even do infinity over infinity, the main piece of information for us is this right here. in the context of limits, 1 over infinity is 0, and 1 over 0 is infinity. Right, that is in the context of limits. So we're going to use these to do our kind of sketchy algebra on all these expressions. First, infinity over infinity. Well, if you think of infinity over infinity as being, let's see, how can we express this? As being infinity times 1 over infinity, right? And then infinity equals 1 over 0. 1 over infinity equals 0. This gives you 0 over 0, which is indeterminate. And now this algebra isn't really algebra, because this isn't valid for the real numbers. But remember, all of this is in the context of limits. And as long as you keep that in mind, all the stuff that I'm doing right now is in the context of limits, then it's all okay. So in the context of limits, infinity over infinity is essentially 0 over 0, just rewritten. Next, 0 times infinity, which you may think would be 0, since 0 times any real number gives you 0. In actuality, it turns into this, because infinity is 1 over 0, which gives you 0 over 0. Because again, we aren't doing real number arithmetic. We are in the context of limits. Let me just add one more color to that. Next up is infinity minus infinity, which you might think is 0, but in actuality, infinities can be different sizes. And to show that it's indeterminate, let's use the fact that infinity is 1 over 0. So infinity minus infinity is 1 over 0 minus 1 over 0. We'll subtract those two. An easy way to subtract is you take this product minus this product over that product. Quick little side note. This is an easy way to subtract, or to add for that matter, fractions. You just multiply this diagonal minus the product of that diagonal over that product. It lets you do arithmetic with fractions in your head. You can just like fly right through it. I did the same trick up here. But you can see infinity minus infinity is just another version of 0 over 0. The ones with exponents are harder to explain. Although 0 over 0 makes sense why that one is indeterminate, because 0 raised to any power is 0, but anything raised to the 0th power is 1. So what's 0 to the 0? Well, it could be 0, it could be 1, it could be the square root of e, it could be anything. And to show that it is indeterminate, we have to do a little more math. Let's assume that the answer of 0 to the 0th power is a. We log both sides. Log a equals log 0 to the 0. Doing that allows us to bring this 0 down in the front. Log a equals 0 times. Now the natural log of 0 is negative infinity, because again, we are in the context of limits. And this function log x approaches negative infinity as x approaches 0. So in the context of limits, log 0 is negative infinity, which means that log a is 0 times negative 1 over 0, which is negative 0 over 0, which again is indeterminate. So if we do some math to 0 to the 0th, it gives us a form that has this indeterminate form. So again, all 7 of these indeterminate forms are really just 0 over 0. Somewhere in those expressions, this is showing up. Let's just finish it off. Infinity to the 0th power we do the same game. We let that equal a, then we natural log both sides. I'm going to put a first now. Properties of logarithms allow us to bring the exponent in front of the logarithm. The natural log of infinity is infinity, because again we're doing limits here, and as x goes to infinity, log x goes to infinity. 0 times infinity is 0 times 1 over 0, which is 0 over 0. And lastly, 1 to the infinity. 1 to the infinity is the most confusing, because 1 raised to any power gives you 1. 1 to the millionth power gives you 1. 1 to the 200,000 million quadrillionth power gives you 1. But 1 to the infinity, you have no idea. And we'll do the same thing. We let the answer equal a. We take the log of both sides. We bring down the exponent in front of the logarithm. We evaluate the logarithm. And you see that we get, not surprisingly, 0 over 0. So 0 over 0, that is the main indeterminate form, because those zeros are making you lose your information.